Welcome, welcome, welcome. Everything is fine. This is ME420, Fundamentals of Manufacturing. And my name is Professor Wield. It is my pleasure to welcome you today in this video introduction to my class. Not there in person, but every class will be live and in the classroom. I'm looking forward to being with each and every one of you. I like to start off each of our class sessions with an agenda so that you know what to expect during the class session, which is 50 minutes. I like to start on time. In fact, I will start on time down to the second as marked by Microsoft time on the internet. And hopefully I'll end on time. My goal is always to end a little bit early, give you a few minutes of free time. And literally it could be 2, could be 3 minutes if we can get through the material, and there's a lot of material. In our courses, we're going to see a lot of videos, and I'm going to share 2 of those videos with you today during our introduction. Let's jump right into our first video. This is about the 4th manufacturing revolution. Very exciting times that we're living in. Exciting times to be in manufacturing.
I'm here to tell you about the amazing 4th manufacturing revolution that is currently underway. It's not as if we've done nothing with manufacturing since the last revolution. Actually, we've made some pretty lame attempts to try to revitalize it. But none of them has been the big overhaul we really need to get us going again. For example, we've tried to relocate our factories offshore in order to reduce cost and take advantage of cheap labor. Not only did this not inspire productivity, but it only saved money for a short period of time because cheap labor didn't stay cheap for long. Then, we've tried to make our factories larger, and we specialized them by product. The idea was that we can make a lot of one product and stockpile it to be sold with demand. This did help productivity for a while, but it introduced a lot of rigidities in our supply chain. Let's take fashion retail. Traditional clothing companies have built these offshore, global, rigid supply chains. When fast fashion competitors like Zara started replenishing their stores faster from 2 collections a year to 1 collection a month, none of them has been able to keep up with the pace. Most of them are in great difficulties today. Yet, with all of their shortcomings, those are the factories we know today. When you open the doors, they look the same as they did 50 years ago. We've just changed their location, their size, the way they operate. Can you name anything else that looks the same as it did 50 years ago? It's crazy. We've made all the tweaks to the model that we could, and now we hit its limits. After all of our attempts to fix the manufacturing model failed, we thought growth could come from elsewhere. We turned to the tech sector. There's been quite a lot of innovations there. Just name one, the internet. We hoped it could produce growth. And indeed, it changed our lives. It made big waves in the media, the service, the entertainment spaces. But it hasn't done much for productivity. Actually, what's surprising is that productivity is on the decline, despite all of these innovation efforts. Imagine that, sitting at work, scrolling through Facebook, watching videos on YouTube, has made us less productive? Weird. This is why we are not growing. We failed reinventing the manufacturing space, and large technological innovations have played away from it. But what if we could combine those forces? What if the existing manufacturing and large technological innovation came together to create the next big manufacturing reinvention? Bingo! This is the 4th manufacturing revolution, and it's happening right now. Major technologies are entering the manufacturing space, big time. They will boost industrial productivity by more than 1/3. This is massive, and it will do a lot in creating growth. Let me tell you about some of them. Have you already met advanced manufacturing robots? They are the size of humans, they actually collaborate with them, and they can be programmed in order to perform complex, non-repetitive tasks. Today, in our factories, only 8% of the tasks are automated. The less complex, the more repetitive ones. It will be 25% in 10 years. It means that by 2025, advanced robots will complement workers to be together 20% more productive, to manufacture 20% more outputs, to achieve 20% additional growth. This isn't some fancy futuristic ideas. These robots are working for us right now. Last year in the US, they helped Amazon prepare and ship all the products required for Cyber Monday, the annual peak of online retail. Last year in the US, it was the biggest online shopping day of the year and of the history. Consumers spent $3 billion on electronics that day. That's real economic growth. Then there's additive manufacturing, 3D printing. 3D printing has already improved plastic manufacturing, and it's now making its way through metal. Those are not small industries. Plastic and metals represent 25% of the global manufacturing production. Let's take a real example. In the aerospace industry, fuel nozzles are some of the most complex parts to manufacture. For one reason, they're made up of 20 different parts that need to be separately produced and then painstakingly assembled. Aerospace companies are now using 3D printing, which allows them to turn those 20 different parts into just one. The result? 40% more productivity, 40% more output produced, 40% more growth for this specific industry. But actually, the most exciting part of this new manufacturing revolution goes much beyond productivity. It's about producing better, smarter products. It's about scale customization. Imagine a world where you can buy the exact product you want with the functionalities you need, with the design you want, at the same cost and lead time as a product that's been mass-produced, like your car or your clothes or your cell phone. The new manufacturing revolution makes it possible. Advanced robots can be programmed in order to perform any product configuration without any setup time or ramp-up. 3D printers instantaneously produce any customized design. We are now able to produce a batch of one product, your product, at the same cost and lead time as a batch of many. These are only few examples of the manufacturing revolution at play. Not only will manufacturing become more productive, it will also become more flexible, and those were exactly the elements of growth that we are missing. But actually, there are even some bigger implications for all of us when manufacturing will find its way back into the limelight. It will create a huge macroeconomic shift. First, our factories will be relocated into our home markets. In the world of scale customization, consumer proximity is the new norm. Then, our factories will be smaller, agile. Scale does not matter anymore. Flexibility does. They will be operating on a multi-product, make-to-order basis. The change will be drastic. Globalization will enter a new era. The east to west trade flows will be replaced by regional trade flows. East for east, west for west. When you think about that, the old model was pretty much insane. Piling up stocks, making product travel the whole world before they reach their end consumers. The new model, producing just next to the consumer markets, will be much leaner, much better for our environment. In mature economies, manufacturing will be back home, creating more employment, more productivity, and more growth. Good news, isn't it? But here's the thing with growth. It does not come automatically. Mature economy will have to seize it. We'll have to massively retrain our workforce. In most countries, like in my country, France, we've told our children that manufacturing had no future, that it was something happening far away. We need to reverse that and teach manufacturing again at university. Only the countries that will boldly transform will be able to seize this growth.
Thank you, Olivier Scalabre, speaking to us from France, sharing some very cool insight into the future. Wow, manufacturing. It drives every aspect of our society. It creates the jobs. It creates our quality of life through improvements in technology, our cars, our smartphones, buildings that we're in, everything manufactured. And the fourth manufacturing revolution coming up, just starting now, creating a huge macroeconomic shift in everything that we've just talked about, in jobs, in quality of life, in productivity. It's exciting times. Before we can jump into the fourth manufacturing revolution, we'll want to spend some time looking at the third manufacturing revolution so that we can get familiar with that. As we jump back to our agenda, I'd like to start off with a little bit about myself, perhaps. I have been in the industry, manufacturing industry, mostly through Hewlett-Packard for the last 35 years. I wanted to get into education for a long time, mostly to be able to help you folks to be successful in your careers, wherever it may take you. I have some current experience teaching manufacturing at University of San Diego, where I teach a manufacturing lab. I teach the lecture class here, I teach the lab class there. I'm also teaching a mechatronics class here at San Diego State. Both those classes, as well as other things that I teach, are brought current by my experience working at Simplexity Product Development. I work part-time and I work there for fun. I do make them pay me. I'm there mostly for my own enjoyment, working through projects, interesting projects of biomechanics, robotics, and with that I can help to bring some experience here to you. I have a master's in mechanical engineering from San Diego State, where my tuition was less than the cost of your parking. And it just kind of shows you it was quite a while ago. I also have a degree from UCSD in chemistry, and you'll see in this first part of the class where I start talking about plastics and polymers, where we're going to bring some of that into the picture. Again, the things that you as design engineers will need to know as you're specifying materials for the parts that you're making. I'm certified in Lean Sigma Black Belt, and that's along with Certified Manager of Quality from ASQ. Those are quality certifications. We're going to have a section in this class on quality. So for those folks that are highly interested in that, something to look forward to. For those folks that maybe need to learn a little bit about that, how does this understanding of quality affect your parts that you're designing and manufacturing? We'll want to look into that. I'm a licensed professional engineer and certified in configuration management. I'm here with the intent and purpose of bringing to you the stuff that I think the design engineer needs to know. What processes are available to make your part? You want to make a part, it's maybe part of a product. Are you going to mold it? Are you going to cast it? Are you going to machine it? What are the different considerations? How would you select the appropriate process? How would you know the design rules for each of those processes? You have to design the part a little bit different for optimization for each of the processes. As I mentioned with quality, how do you make sure that the parts that are being made from your design will work? There's variations in life, and will your design be able to withstand the normal variations of manufacturing? And how do we understand what those variations are and what the capability of the process might be? This class is about design considerations. It's not about manufacturing optimization. There's manufacturing engineers that are working on that and will help you. It is about part fabrication technologies, plastics molding, 3D printing. It's not about factory design. Quality control and specifications, as I mentioned, but not about implementing quality control in a factory. It's about mechanical parts used in products. We're not talking about food and chemical manufacturing. Mechanical parts. Mechanical engineering, not systems engineering, manufacturing, industrial engineering. If you wanted to study those, you would have majored in those. Or maybe you are as a double major. In this class, we're focused on mechanical engineering, looking at broad qualitative process knowledge. This is not like your other engineering classes. We're not about, here's an equation, and now I'm going to teach you how to solve it, and then I'm going to test you on how you solve that equation. It's more about understanding the processes. There are some equations in here, and they're based on the mathematics of arithmetic, maybe a little algebra. Nothing more advanced than that, but still there to help you to understand the logic of manufacturing. Talking about parts that go into assemblies, material and process selection. And again, areas that are relevant to mechanical design engineers, topics that I wish I had known when I graduated San Diego State and started working as a design engineer. The topics that I wish the engineers that I had hired already knew when they came to me, so I wouldn't have to spend the time teaching them. This course is 15 weeks. There'll be 10 or 11 projects to do. You could call them homework, we could call them assignments. They're really mini projects. There'll be 3 midterms and a final, but the final's not really comprehensive, so it's kind of like 4 midterms, so we don't have any high stakes tests here. Here you see the topics that will be discussed and the number of lectures spent on them. More on that later. There is some reading. There is a textbook. I think it's kind of optional. In fact, if you look closely at the Amazon review for our textbook, you may see some key points here. I needed this for a manufacturing process materials class. Really ended up not using it much. It contains a ton of information and goes into great detail for some of the most minor things. Some of it great to know, some of it kind of useless. Found myself just skimming through the chapters rather than reading them. Overall, if you need this book for a college class, see how the info in the book and the material and what your professor teaches line up. If the professor looks like he's just skimming through, then you probably don't need it. You might save a few $100. I don't think that books cost that much. But for those folks that like textbooks and want a little reading to supplement, this is the book that I'm following. And these are the chapters in that book, how they correspond to those topics which I just put in front of you, which we're going to go through throughout the course. You can get different editions of this book, whatever is helpful, or don't get the book. I don't assign any homework out of the book. It's all of the information that you need is provided in the lectures, which you should attend 100%. And the lectures are based on the slide sets, which you have access to even right now. We'll be taking a glance through Canvas and we'll show you how to navigate that part of our course. Prerequisite ME420. As I mentioned, the homework. We're looking at quizzes. So there will be quizzes. The quizzes that I do are maybe not like the quizzes that you have in your other courses. They count for 5% of your grade, as you can see here. There could be quizzes that are daily quizzes where the answer doesn't matter. It's about the discussion that goes with it. But if you do answer, you get credit. And it's also a way of finding out whether you're there and present. in the class. There are also online quizzes, multiple choice quizzes, which are kind of like the same format as the midterms. Except with these quizzes, you can take them as many times as you want until you get the right answer. And I'm amazed at the number of people that don't get 100% on those quizzes under those terms. I mentioned the midterms and the final. The final will be as scheduled. It's I think it's about a 2-hour final, 1 hour 50 minutes, but it's the same weight as the midterms. There's no high stakes tests here that you need to worry about. This quiz is more for learning than evaluation. I'm not sure how I'm going to do the quizzes this semester. In Zoom, we had Zoom polls, thought-provoking questions. In live classes, sometimes it's just the equivalent of coffee and treats day. Sign your name, get the points on a sign-up sheet. There's an example of an online quiz there. Could be translated into a Zoom poll. We'll see how that works. You'll see in the syllabus section on diversity. Diversity is important to me. I value diversity. I value the diversity in all of you. This is a safe place for LGBTQ community, students of all faiths, veterans, nationalities. I enjoy listening to the experiences of my diverse students. You'll see in Canvas a course outline. This is something that you should pay attention to. It will change. I do about 8 versions of these throughout the semester. Starting off looking like this, give you a view as to what to expect each day. Maybe more importantly, when are the exams going to happen? When are those project assignments due, the 10 or 11 that I spoke about earlier? It's all in this manufacturing course outline, manufacturing processes course outline. I'll show you where to find that in Canvas. And speaking of Canvas, let's take a Canvas tour. Here I'm showing the home page of ME420 Canvas, and I'll take you on a short tour of the contents. So on the home page you may have seen my welcome message, and I do mean that you're welcome. I've extended this welcome earlier in the summer for those folks that maybe wanted to take a look ahead, were a little bit curious, or maybe those folks that wanted to get a head start on the material. The slides are located in here. You can see what's coming up. I will make revisions of those slides as we go throughout the semester, but always giving you some idea of the contents to come as you may desire to study ahead. And the syllabus, we can see in the syllabus you'll find our contract between myself and you as a student, the course contents, the rules are, prerequisites for coming in, learning objectives, all those things. I think the relevance material I have included in the slides, which I just shared with you. The contents of the course as you see them here. Class policies, examinations, and if you scroll to the end, you'll see what the breakdown is for the grades. Grades are a way of measuring your comprehension of all the material that's presented. There is an extensive amount of material presented. Grade breakdown in this class is intended to be a little easier than your core classes. However, there will be a fairly decent spread with the number of students that we have in this class. I can guarantee you the average will be right in the middle of the B's. That is, half the class will be a B and higher, half the class will be a B and lower. This class may or may not be a priority for you. It is intended to be flexible around your core classes, flexible around your life. If you just pick up information from one or two of the topics that I present, I think you'll find it useful in your career. If you can pick up all of them, not only will you do well on the exams, but have that much more breadth of information. The core part of the Canvas is in the modules section. And as we flip over to modules, you'll see some student resources information that's there for you. As we get down to the top section, instructions, introduction to manufacturing. As we get down to the top section, you'll see course schedule and other information. And this is where you'll find the course plan that I spoke about earlier, and the one that will be updated from time to time as you and I kind of make some choices. What works for you? Maybe an exam on a Monday is not good. Maybe you'd rather have it on a Friday. Maybe this week isn't too good because you've got other work in your other core classes. We'll move things around. And here's where you'll find the most up-to-date on the schedule all the way through the whole semester, including the exam, final exam at the end, and all the 3 exams in the middle, quizzes, online quizzes that are due that we talked about. In the modules section, the class is broken down into modules. This first module is the Introduction to Manufacturing, and that's what we're in right now. Not just the introduction to this class, but the Introduction to Manufacturing, which we'll also cover in the next live session when we're able to get together. That would be slide set 1.2. And as you click on these, the PDF for the slide set should pop up. I may make changes, late changes, and I'll always update those according to the lecture that was provided. Our first module, module 2, divided into 2 sections since it's very lengthy, getting into polymers and thermal sets and plastic molding and other types of shaping processes with plastics. If we go back up to assignments, you'll see under assignments these projects that I've been talking about. Probably 10, maybe 11. You'll see them here, and they're outlined for you. I may make changes in these as well, but these are what we have. In the first one, what resin or polymer or plastic would you use for a particular application? I'll give you some applications, I'll give you some plastics. You do some work and figure out how you would match those up. You're going to pick a plastic part for project number 2, any part that's within your environment, and we're going to look at that part in detail. There will reveal quite a bit about how it's made, what material it was made out of. You'll be recognizing tooling marks and other marks on that plastic in a concise report format, reporting on what you've found. And as we go through all of these, they are intended for you to look at parts in your environment wherever possible. For most of these, there are also some relevant assignments in terms of root cause analysis, which may be useful for your senior project. If you're having some problems at that time, I'll give you some techniques for solving problems that look very difficult in your designs and an approach to take when you run into those. So that's our Canvas tour. A lot of good information there. In the agenda, you may have seen another topic that's coming up next. This topic is key success factors, and I'm not talking about how do you get an A in this class. I'm talking about how do you succeed in life? How do you succeed in your engineering careers? How do you succeed in quality to drive for high quality performance of products without failures. Let's take a look. In the first key success factor to life, just show up. What could be easier? When we are in class live, just show up. If you're there in person, you're going to learn a whole lot more, be able to interact with others. Maybe you're going to network around. Maybe you're going to find somebody or something you didn't know before. This is not only for this course, but everywhere in your life. Just be present, be on time, and people will reward you. My job, I mentioned I do program management at Simplexity Engineering. That was because I showed up at a lunch that I didn't really feel like going to. But when I did, they said, you know what? Now that I see you here, you would be perfect for this job. Would you be interested? Tell me about the job. And I was, and I still am. Just show up. Next key success factor in engineering, visualize. Don't memorize. If you memorize, you will forget it. If you visualize, those pictures in your brain will tell you a lot more. This is also a key success factor for this class. There is so much material here that you can't memorize all the facts. You need to visualize what's happening in reality. If we're talking about an injection mold, you have to visualize those pellets of polymer going into the barrel, being mixed by the reciprocating screw, being heated by the heater bands, and becoming a molten flow that gets pressed through a sprue into a gate, going through runners into a part that filling up every part of that cavity, and then cooling down. And of course, with that visualization, we start to think, wow, how do we cool it down? How fast can we make a part? What is the cycle time, the cost of the part? Is those stresses going to cause it to warp? All this through your visualization skills. In any aspect of engineering, when you're doing design work, you have to visualize that end product. I had the opportunity to speak to the third founding member of Hewlett-Packard, Barney Oliver. He was the head of HP Labs, and he told me you just have to visualize what is the perfect product at the end and then see how close you can get to it. Visualize. And in quality, something that's maybe a little counterintuitive. If you want to produce quality products, you've got to value failure. Value failure. We're going to talk a little bit more about that, but every defect you find is like finding buried treasure. You want to look for it. You want to cherish the finding of that treasure. You want to congratulate your coworkers if they have failed. This is so great that you found this. Can you imagine if we hadn't have found this and that product had made it out into the field? It would have been so much of a problem. Now, some students sort of value failure a little different. Certainly mistakes that you make in class could lead to failure. That's not the kind of failure I want to see. I want to see each and every one of you do well here. But when you're doing product testing, you're looking for failures, and you're going to be happy when you find them. As we start to wrap up this introductory session, I want to share with you a video from Proto Labs. A lot of our videos are going to look like commercials. The companies that produce these want you to be their customers. And they're good suppliers to know. All the suppliers that we see and any suppliers that approach you, they are trying to offer you solutions that will help you to produce quality, low-cost products. But I like this video because it takes us on a tour of several manufacturing functions throughout Proto Labs' extensive factories. Let's take a look.
Since 1999, Proto Labs has been changing the traditional rules of manufacturing. Due to our digital approach to quoting and manufacturing, as well as highly experienced staff, ranging from software engineers to mold technicians, we can manufacture custom prototypes and low-volume production parts in as fast as one day. And yes, that includes traditional manufacturing processes like CNC machining and injection molding, in addition to 3D printing. Find it hard to believe? Let's take a tour through one of our manufacturing facilities to see firsthand how we transform a customer's CAD model into physical parts. It all starts with computing power. In fact, this was one of the world's most powerful computer clusters just 5 years ago. It has since been surpassed by the likes of Google and large government agencies, which will concede, but it still remains the most advanced system in the manufacturing industry. Once a customer uploads a design at protolabs.com, it's analyzed using our proprietary software, and an automated quote is generated and sent within a few minutes to a few hours. The online quote contains real-time pricing, not a budgetary estimate, as well as interactive design feedback to improve manufacturability. With a traditional manufacturing company, this process can take many weeks, but with our automated quoting software, a customer can assess, iterate, and validate multiple part designs in a single day if needed. Once an order is placed, digital instructions are sent to an interconnected network of manufacturing machines on the production floor, including EDM machines, mills, lathes, plastic and metal 3D printers, and injection molding presses. Right now, you're looking at more than 20 injection molding presses and 90-plus CNC machines milling away at what will soon become molds. At this location, we conduct injection molding sample runs, so this is only a fraction of our total number of presses. At our injection molding facility in Rosemount, Minnesota, we have around 100 presses that handle our production runs, which routinely produce volumes as low as a few hundred, often reach volumes of 25,000 parts, and occasionally make part runs over 1 million parts. The molding process begins by milling a block of metal into a mold. Typically, we fabricate molds from aluminum to reduce manufacturing time and cost. But sometimes we turn to steel, depending on the part's geometry, material, or quantity. And then, if required, the mold stops at an electrical discharge machine, or EDM machine, for a final touch-up. Whether or not EDM is necessary depends on the part geometry and other characteristics. Once machining is complete, the mold goes through the build room for hand polishing and pin placement, and then it's brought out to the press. After parts are molded, they undergo a quality inspection and are shipped out to customers. This entire process can happen within days. As we move down to the floor, we'll pass by our liquid silicone rubber room. Although not a certified clean room, we do keep it isolated from the rest of the facility to ensure the highest quality. Right now, we have 10 presses dedicated to liquid silicone rubber molding, in addition to producing silicone parts in standard, optical, medical, and fuel-resistant grades, and in multiple durometers. These presses are vital to our overmolding process, which creates two-material thermoplastic parts. Next, let's go check out our machining area. On our way, we'll pass by our stock of thermoplastic resins, raw metal material for molds, and one of our mold storage areas. Every customer mold is stored indefinitely at Proto Labs, and every 2 years or so, we check in with past customers to see if they would like us to continue storing their mold. Now we've entered our CNC machining area. Note that in this area, we are machining parts, not molds. Here, we have approximately 200 CNC mills and lathes, offering 3- and 5-axis milling, as well as turning with 3-axis live tooling capabilities. In CNC machining, our highly automated process and design analysis software are keys to us delivering machine parts faster than anyone else. It's not uncommon for us to receive a customer's design and ship the finished part within the same day. Let's wrap up our tour with a quick look at the shipping area. As you'll see, when it comes to shipping at Proto Labs, less is more. We don't require much storage room since we ship parts as fast as possible. Even after we ship parts out, we retain the digital part files so customers can always come back and easily order that same part on demand. Thanks for joining us today. We hope our quick tour helps shed some light on how we might be able to lend a manufacturing hand on your next project.
Well, thank you, Proto Labs, for that tour of your factories. I should mention that when you are looking for fast turn prototypes, they are going to take some shortcuts. Are you going to get sharp corners or radius corners? Are you going to get that aluminum based tool or a steel tool? And what does that even mean for injection molding? We're going to learn about that throughout the first part of the course. I mentioned homework in the agenda. I don't know if you caught that. Well, the homework here is really not so much homework on this first day, but I did want to point out that Proto Labs, if you email them, maybe give them your name as a future engineer that they might contact to hope to get some business, we'll send you these cool things. They have a number of cool things they'll send you all for free. The one on the left, a design cube. It'll show you good and bad designs for your features in plastic parts, which may be ribs, bosses, slides. We'll learn a little bit more about those design features in our course. And the one on the right is a little plastic toy injection mold, which has a slide inside, an internal slide. It has a sprue, which I mentioned is that channel that gets the plastic from the nozzle of the injection mold into the runner system of the parts. You can see that and visualize that in this toy mold where it opens and closes. My only issue with these folks is it's free, but it takes a long time. Sometimes people get these way after we're finished with the plastics section. So if you're interested, there's a link in the slides you can get from Canvas in Module 1, Introduction 1.1 slide set. So take a look. As I said, it's optional. So thanks for joining me today on this video introduction of ME420, Fundamentals of Manufacturing. I look forward to seeing each and every one of you in class. Until then, happy manufacturing. Wow, manufacturing. Wow, it's the fourth manufacturing revolution. Making it important to teach manufacturing in the universities again. You gotta love that. Manufacturing drives every aspect of our society. It creates the jobs. It creates the So let's jump right into our first video. This video talks about the fourth manufacturing revolution. We want to find out, what does that mean? Most of our time will be in studying the third manufacturing revolution. What does that mean? Who cares? I like to start off each of our class sessions with an agenda so that I can let you know what to expect during this period and see if there's any expectations. So feel free to peruse. Key success factor in your life: show up. And if you're showing up in class and you're showing up if you're showing up in class, you're meeting this key success factor. If you're showing up at your group meetings, so thanks for joining me today in this video introduction to ME420, Fundamentals of Manufacturing. I'm looking forward to seeing you in class coming up soon.